physical activity from the elderly people. So some of the trends we are actually looking in these exergaming scenarios is we need to improve this sustainable motivation in users, because they are normally playing the exergames, but in the very first sessions they are actually getting bored in playing these exergames. The second one, the idea is try to give some physiologically positive behavior to that, because we need to be constantly recording this physiological data in order to avoid certain bad states, like for instance over-exercising the people. And the idea is how can we actually make these exercise video games more adaptive to the users. So, and our, it's going to say, ground truth for this is that the people in physical exercise call the aerobic exercise session. So this is our kind of a target state. The idea is, so we need to exert people in a certain target level in heart rate. We're using heart rate data for this. The idea is they normally have a maximum heart rate level in which they are supposed to be exerted. So the idea is sustain people in this specific region, a specific target level in which the cardiovascular benefits of doing exercise that's supposed to be optimal. So this idea is, with this main goal, we started designing a physiological computer system that will use this biocybernetic adaptation, this biocybernetic loop, by using some data from the heart rates and cardiovascular data. So, experiment was like this. So this is a small video that is going to summarize some of the things we were doing. So some of the extra games we are normally developing for the elderly people. They are normally playing in a really engaged way. But at the same time, we notice that some of these extra games are not actually really well designed for produce some of the recommended levels of exercise. Sometimes they are over-exercising, or sometimes they are not really getting those target levels. So the solution that we proposed was trying to use some of the these heuristic adaptive rules, like for instance, if the heart rate is less than the target heart rate level, then it's going to try to increase or decrease the difficulty level of the game. The game again was a really simple adaptation of the pong. And then we compared always actually the heart rate of the cardiovascular responses of users during our exercise, our adaptive, physiologically adaptive extra game versus the conventional exercise that they are normally doing at the gym. So we noticed in our experiment, and I will show you later on, that those kind of adaptation can actually push people to exert more time in that specific target level, that specific target zone, in which those benefits of make exercise can be actually optimal. So for that, we also developed this software that we are going to be using today. That is basically a very simplistic approach to create these heuristic adaptive rules. This will allow us to actually create more or less an intelligent adaptation based on physiological data. So I will briefly explain to you how we did this kind of experiment and the setup itself. We first of all designed an extra game based on the classic Pong. We used some positive feedback, to stimulate, to get positive stimuli to the user, but also bad feedback once they are actually losing the balls. In the experiment setup, we just use a floor projection, as you can see in the pictures. And we basically make two different layers of adaptation. The first is an adaptation that we call gameplay adaptation, which is not depending on the physiological data. So once the user is missing balls, the paddle of the game will increase, and vice versa. And once you miss 3 consecutive balls, the ball velocity will decrease. So this is a way that we are using to actually create some adaptation based on game metrics, not only in the physiological data. In the second stage, in the second layer of adaptation, we basically build our biocybernetic loop. So in this biocybernetic loop, we actually started from the collection stage. In the collection stage, we basically make an initial configuration of the user. So the idea is we make the computation of the target heart rate. That computation is depending on the age of the users and the heart rate during resting states. We took like 5 minutes of the resting state of the users. Then we make a signal acquisition, and we use a pretty simplistic and wearable sensor for that. We use it as a smartwatch, and we actually compute the heart rate, the average of the heart rate during 30 seconds. So in the analysis stage, we basically take a look over the recommendation of the American College of Sport and Medicine, and they say that for our population, the elderly people, they actually they should exert 40 to 70 of this heart rate reserve, which is the difference between the heart rate maximum and the heart rate during resting, and we took exactly the midpoint of that. So for this optimal cardiorespiratory behavior, we should push users, our users to actually exert to that specific target level. So then we create our heuristic adaptive rules. If this heart rate during this 30 seconds is bigger than the target heart rate, then we are going to reduce the difficulty level of the game. And we are going to make the same, we're going to do exactly the same for the increase in the difficulty. In the translation stage, so we are finally making the effect happening in the game adaptation. And in this case, we are using ball. We are just changing the ball velocity to actually try to push user to exert to that specific case. And we use a proportional controller for that. Proportional controller, quite simple. We just took the target heart rate level and we subtract the current heart rate level during these 30 seconds. And we make the adaptation, which means the ball velocity will change proportionally considering this difference. So we took 15 community with older adults, really active older adults. Some of them, they didn't have any kind of experience with video games. We took some inclusion criteria, considering some of the exercise, sport, science tests for that, the senior fitness test. And we got a couple of people searching. So we developed this software to actually facilitate the processing of the signals. We compute some heart rate variability metrics for that in order to compare both conditions. For the protocol, we took this control condition in which they are basically doing the same exercise that they normally do at the gym, like playing with these balls or playing with sticks and making some aerobic exercise. And for the adaptive exerpong, we took the heart rate during resting, the first 5 minutes. Then we were making some stretching in order to warm it up. And then they play the exerpong during 20 minutes. We compared 20 minutes over the people playing the exerpong versus the 20 minutes over people like doing the conventional exercise. So we also use a couple of scales, like subjective scales, to measure the level of exhaustion, like physical exhaustion of people. So some of the results that we took from the experiments is actually the participants spend significant more number of minutes in the targeted zone with the biocybernetic loop system, which means we could from the 20 minutes, those more than 40% of participants, they actually increase the time they spend in this targeted zone. As you can see, there's like two different curves of profiles. So it's like an average curve for that. In the first one, you have the conventional exercise. So we have the targeted level. This is this dotted line, red dotted line. And during the conventional, you can more or less see that they never got the heart rate maximum, which is good for them, but they are pretty far from the targeted zone. So as you can see here, it's more or less quite less organized or less stable than in the heart rate adaptive way. By using our Biocybernetic loop implemented in the Exergaming, we actually could push people to stay closer to the targeted zone, as you can see here. So we have a lot of standard deviation considering the different differences of ages that we have, but you could see more or less that this specific profile is better in terms of how close people are from the target zone. So we also compute some heart rate variability parameters, and they show some values in the standard deviation of these normal peaks and the root mean square as well. All of them, once compared with the conventional exercise, both were lower values. So we got lower values of heart rate variability during this adaptive Exergaming. And we have some time and frequency domain variables in which we can see some differences, especially in the very low frequencies for the adaptive Exergaming. We also took some subjective measurements, which we asked people basically if they are gonna they will play the game, if they actually enjoy the experience, if they have some certain level of bored playing the game. And as you can see here, like the levels of enjoyment of people playing the game versus the conventional exercise, it was better than the actual how competent they felt playing the game. So there's some interesting subjective analysis as well from this experience that we got. So as a way to conclude our experiment, as a way to show how effective was this Biocybernetic loop applied in this cardiovascular adaptive application. So it's a good way to complement this adaptation. So at some point, if you just, in games or in Exergames as well, if you just put the adaptation, the physiological adaptation layer alone, probably that's not going to be sufficient, that's not going to be enough to provoke a good experience in the users. So we choose to actually distribute the adaptation. One, just considering the game metrics, like for instance, if they are losing balls or they are getting the balls. And the second one, the second extra adaptation layer, we use the physiological adaptation. So we could more or less balance both different types of adaptation. We also at the end, we realized, after having different iterations of our software, that a very simplistic approach as a proportional controller could also be a success as a more complex system, like for instance trying to use some machine learning approaches or some non-heuristic adaptive rules. And now our idea is how can we actually measure the long-term effects of this Biocybernetic loop. How can actually this adaptive system can be good to provoke changes in the cardiorespiratory fitness of people if we extend the use, like for instance, twice per week. So you're gonna try to check this. So for the heart rate variability interpretation, it's quite difficult because most of the literature establishes that bigger the heart rate variability, a bigger heart rate variability is a good signal of a good health status. But in this case, considering that we are trying to control the heart rate responses to a certain specific targeted zone, so we conclude that a more controlled heart rate variability around this targeted will actually reduce the exercise associated, some of the risk associated with the over-exercise. So in the spectrum, we also got some conclusions regarding the very low frequencies, and what it is that the people can be encouraged to actually not only get out this specific target zone, but also try to sustain this behavior during the whole cardiorespiratory session. So we got some troubles with the measuring heart rate level with the smartwatches, especially because the people are normally doing exercise, and some of the variables, or there's some variability regarding the measurements. But we also found some interesting comparison between this heart rate from smartwatches and from some other ECG and polar chest straps, and we got pretty similar behaviors from both sensors, so we managed to work with that. This is some of the take-home messages. This Biocybernetic adaptation for us has this kind of potential to maybe try to maximize the time that people are exerting this targeted heart rate zone. So this heart rate variability analysis by means of smartwatches is quite not. It shows to be accurate enough to assess some of the heart rate variability changes. Yeah, again, the variability around this targeted heart rate zone is still something that we have to discuss in the next experiments. So this first example or use case I showed to you, we actually put a physiologically adaptive layer on top of a game in order to increase or push users to reach certain targeted zones in which the literature establishes that there is an optimal behavior for the cardiorespiratory fitness in elderly people. So